Imagine you are playing a board game where sometimes a piece falls off the board. Instead of the whole game stopping, you have a rule that says if a piece falls, put it back on the start and keep playing. Structured exception handling works the same way for programs. Why we need it? Without it, a single mistake like dividing by 0 would crash the whole program, just like the board game would end if a piece fell. Benefits: clear separation. Normal code, the happy path stays clean while error handling lives in its own block. Safety: errors are caught close to where they happen, preventing hidden bugs from spreading. Recovery: the program can decide how to recover, retry, give a message, or clean up resources, instead of just quitting. Readability: future readers see try catch finally and instantly know where problems are treated, just like a rulebook tells you what to do when a piece falls. Practical tip: because the checks are cheap, always use the correct specifier. You gain safety for free. Kid-friendly analogy: think of a school playground. The rules who may use which equipment are posted on a board before recess. The teachers, which represent the compiler, read the board and stop kids from breaking the rules right away. Once recess starts, which represents the program running, the kids just play. They don't keep checking the board every second. The board only matters when the teacher is watching, which represents compiling. Explanation: a try-catch finally block is like a safety net with 3 parts. This is the area where you attempt something risky like climbing a ladder. If everything goes well, you finish the block and move on. Catch: if something goes wrong while you are in the try part, control jumps to a catch clause that knows how to handle that specific kind of problem, just like a friend catching you if you slip. You can have many catch clauses, each for a different exception type. Finally, this runs no matter what, whether an exception happened or not. It is perfect for cleaning up, closing a door, putting away tools. Syntax example: Java like : try open brace, int result equals dividend divided by divisor, risky operation, close brace catch open parenthesis arithmetic exception close parenthesis open brace, system.out.println open quote oops cannot divide by 0 : plus get message open parenthesis close parenthesis semicolon, close brace finally open brace, system.out.println open quote finish the division attempt quote semicolon, close brace. What happens if divisor is not 0, the code inside try runs and then finally runs. If divisor is 0, the arithmetic exception is created, the catch block runs, then finally runs. The program never crashes, it just follows the path we defined. Practical tip: because the checks are cheap, always use the correct specifier. You gain safety for free. Kid-friendly analogy: think of a school playground. The rules who may use which equipment are posted on a board before recess. The teachers, which represent the compiler, read the board and stop kids from breaking the rules right away. Once recess starts, which represents the program running, the kids just play. They don't keep checking the board every second. The board only matters when the teacher is watching, which represents compiling. Explanation: when you need a special kind of error that the language does not already have, you create your own exception class. Think of it as designing a new kind of warning card in a game. Steps to design a custom exception. Step 1. Choose a base class. Most languages have a generic exception or throwable class. In Java, you extend exception. In C# you extend system.exception. Step 2. Give it a clear name. The name should tell what went wrong. For example, insufficient funds exception. Step 3. Add useful data. You can store extra fields like the amount that was missing, so the catcher can give a better message. Step 4. Provide constructors. At least one that takes a message string, and optionally one that takes a cause, another exception. Simple Java example. Public class insufficient funds exception extends exception. It declares 2 private final double fields, balance and needed. It defines a public constructor that takes double balance and double needed, calls super with the message balance is less than needed, and assigns the parameters to the fields. It also provides public getter methods get balance returning balance and get needed returning needed. Now any method that discovers a shortfall can throw new insufficient funds exception with current and required. The caller catches it and can show the exact numbers to the user, making debugging easier. Practical tip: because the checks are cheap, always use the correct specifier. You gain safety for free. Kid-friendly analogy: think of a school playground. The rules who may use which equipment are posted on a board before recess. The teachers, which represent the compiler, read the board and stop kids from breaking the rules right away. Once recess starts, which represents the program running, the kids just play, they don't keep checking the board every second. The board only matters when the teacher is watching, which represents compiling. When an exception occurs, the program does not just stop, it unwinds the call stack, looking for a catch block that knows how to handle it. Think of a stack of dolls. You remove the top doll, then the one below, until you find the right size doll that can hold the problem. Propagation rules. Search upward, starting from the method where the exception was thrown. The runtime checks each surrounding try-catch block. If none, it moves to the caller method, and so on, until it reaches the top, often the main program. Matching type. The exception will be caught by the first catch, whose declared type matches the thrown object or one of its supertypes. Uncaught exception. If the stack is fully unwound without a match, the program terminates or the runtime prints a stack trace. Stack unwinding. While moving up the stack, the runtime also runs any finally blocks on the way out, ensuring resources are released. This is like closing every open door while you walk back to the front of the house. Visual example. Main open parenthesis close parenthesis top of the stack. Read file open parenthesis close parenthesis calls parse open parenthesis close parenthesis. Parse open parenthesis close parenthesis throws format exception. Parse throws format exception. No catch inside parse, so the runtime pops back to read file. If read file has a catch format exception, it handles it, otherwise it keeps unwinding to main. Practical tip: because the checks are cheap, always use the correct specifier. You gain safety for free. Kid-friendly analogy. Think of a school playground. The rules who may use which equipment are posted on a board before recess. The teachers, which represent the compiler, read the board and stop kids from breaking the rules right away. Once recess starts, which represents the program running, the kids just play, they don't keep checking the board every second. The board only matters when the teacher is watching, which represents compiling. Defensive programming is like wearing a helmet before you ride a bike. You anticipate possible problems and stop them before they cause a crash. When to throw. Invalid arguments. If a method receives a value that makes no sense, for example a negative age, throw an illegal argument exception. Violation of invariance. When an object's internal state would become inconsistent, raise an exception to stop it. External resource failures. If a file cannot be opened, throw an input-output exception. Where to throw. Place the throw directly after the check, so the error is reported at the exact line where the problem is detected. This makes the stack trace short and meaningful. Example: Java. Public void set score int s open brace. If s less than 0 open brace, throw new illegal argument exception with message score cannot be negative colon space s close brace. This dot score equals s semicolon close brace. If a caller tries set score with -5, the method immediately throws, and the caller knows exactly what went wrong. This is better than letting the negative value silently corrupt later calculations. Practical tip: because the checks are cheap, always use the correct specifier. You gain safety for free. Kid-friendly analogy. Think of a school playground. The rules who may use which equipment are posted on a board before recess. The teachers, which represent the compiler, read the board and stop kids from breaking the rules right away. Once recess starts, which represents the program running, the kids just play, they don't keep checking the board every second. The board only matters when the teacher is watching, which represents compiling. Explanation: people sometimes think exceptions are slow, like calling an ambulance. In reality, they are fast when they don't happen, but a thrown exception does cost extra work, because the runtime must build a stack trace and unwind the stack. Guidelines for performance. Don't use exceptions for flow control. Do not write code that expects an exception to happen in the normal path, for example using try-catch to test. If a file exists, use normal checks if file exists. Throw only when truly exceptional. If the situation is common, return a status code or optional instead. Reuse exception. Objects sparingly. Creating a new exception every time can allocate memory for very hot loops. Consider pre-created exceptions rarely needed. Keep catch blocks. Small complex logic inside a catch makes debugging harder and may hide the original cause. Rule of thumb: think of exceptions like fire alarms. You only want them to ring when there is a real fire, not every time you light a candle. When used correctly, they keep the program safe without slowing it down. Practical tip: because the checks are cheap, always use the correct specifier. You gain safety for free. Kid-friendly analogy. Think of a school playground. The rules who may use which equipment are posted on a board before recess. The teachers, which represent the compiler, read the board and stop kids from breaking the rules right away. Once recess starts, which represents the program running, the kids just play, they don't keep checking the board every second. The board only matters when the teacher is watching, which represents compiling. You have a divided by b. If b equals 0, the result is undefined. If a or b is very large, the result might not fit in an integer overflow. Public integer safe divide with parameters integer a and integer b open brace. If b equals 0 open brace, throw new arithmetic exception with message division by 0 close brace. Close brace. Integer result equals a divided by b semicolon. If a equals integer minimum value and b equals -1 open brace, throw new arithmetic exception with message integer overflow close brace. Close brace. Return result semicolon. Close brace. The method checks the precondition b not equal to 0. If it fails, it throws an arithmetic exception. The caller wraps the call in a try-catch so the program does not crash. Instead, it prints a friendly message. Public void demo open brace, try block open brace. System.out.println with safe divide 10,0 close parenthesis semicolon. Close brace, catch arithmetic exception e open brace. System.out.println with string caught problem colon space plus e dot get message close parenthesis semicolon. Close brace, close brace. Overflow example multiplication. Mathematically c equals a times b. If a equals 1 million and b equals 3,000, the true product is 3 billion, which exceeds the maximum integer 2,147,483,647. The code can detect this by casting to long first and comparing. Long prod equals cast long a multiplied by cast long b semicolon. If prod greater than integer maximum value or prod less than integer minimum value open brace. Throw new arithmetic exception with message multiplication overflow close brace semicolon. Close brace. Using exceptions, the rest of the program can decide what to do, maybe use long values or show an error to the user. Practical tip: because the checks are cheap, always use the correct specifier. You gain safety for free. Kid-friendly analogy. Think of a school playground. The rules who may use which equipment are posted on a board before recess. The teachers, which represent the compiler, read the board and stop kids from breaking the rules right away. Once recess starts, which represents the program running, the kids just play, they don't keep checking the board every second. The board only matters when the teacher is watching, which represents compiling. Testing exception flows is like rehearsing emergency drills. You purposely trigger the alarm to see if the exit routes work. Unit test patterns. Expect exception. Most test frameworks let you declare that a method should throw a specific exception. Assert throws arithmetic exception class, lambda safe divide 10,0. Verify message and state. After catching the exception, check its message and any side effects, for example a log entry. Mocking resources. Use a mock object that throws an exception when called, for example a file reader that throws input-output exception. This lets you test the catch finally logic without real files. Debugging tips. Read the stack trace. It shows the exact line where the exception originated and the path taken. Break on exception. In IDEs enable break on throw, so the debugger stops the moment any exception is created. Log early. Add logging inside catch blocks logger.error failed, because to keep a record even when the program continues. By writing tests that deliberately cause errors and confirming the program recovers correctly, you ensure that the exception handling you built is reliable. Just like practicing a fire drill, make sure everybody knows the exit route. Practical tip: because the checks are cheap, always use the correct specifier. You gain safety for free. Kid-friendly analogy. Think of a school playground. The rules who may use which equipment are posted on a board before recess. The teachers, which represent the compiler, read the board and stop kids from breaking the rules right away. Once recess starts, which represents the program running, the kids just play, they don't keep checking the board every second. The board only matters when the teacher is watching, which represents compiling.